Welcome, everyone, to our latest edition of the Reimagining Mobility podcast series. I'm here with Brian Moran from our California Tech Center. He's a chief engineer there for us for many years now. And Brian, today I want to talk a little bit about the industry specifically related to batteries. First, kind of give me your general view. What are the challenges today? Where do you see solutions coming up in the future? And then I want to sort of transitioning over a little bit into our very exciting program that we've done for the aerospace industry and soon going into space then as well. So I kind of transition over that. But first of all, batteries, we've done lots of them. In California, we oftentimes do very advanced type battery type technologies or programs. So tell me a little bit, where do you see on a high level the battery technologies are today with the challenges, and where do you see it going into the future?
Yeah, certainly. I mean, we all have to take it with a grain of salt where batteries are today compared to where they were in the past. I can remember a day, when a 40-mile electric vehicle was actually pretty darn good, and you were slinging lead acid around and hoping that you'd get a few hundred cycles at most. So we've exceeded those boundaries quite handsomely. I actually think that at least on the automotive side, obviously, cost and integration is the king there. We're sort of in the performance wars right now. We've seen, with Tesla setting new boundaries on performance. There's been a lot of focus in on 0 to 60 times and top speed and all that kind of stuff. But I think that we're going to be entering an era here pretty soon where it's the baseline vehicle. Not everybody can afford a $75,000 to $100,000 vehicle. So you're seeing companies, like BYD coming out with I don't want to say muted technologies, but more for the everyman. Kind of like LFP type chemistries. It's about large volume production. It's about ease of packaging and safety, as well as getting just the cost per kilowatt hour down, the volume down. Because for electrification to really make a dent in the market, it's got to be affordable for everyone. So I think that while the trends will still continue to be more power, more energy, I think it is more the practical aspects of integration, safety, and cost that are still going to be the king. So on the automotive side, for sure.
Sure. You mentioned an interesting thing, right? The race for whatever EVs that can go faster and faster from 0 to 60. I mean, we've seen it first with Tesla, and it's frankly extremely cool and fun to drive. We've seen it with Lucid, that has one that's very fast as well. We see it with a company like GM, for example, even with the Hummer, right? A heavier vehicle that still has a tremendous acceleration. We see it with the Ford Lightning pickup truck now, very fast, from 0 to 60 as well. Do you see an end to that? Is this just, the OEMs are trying to make an EV cool? Is this something that ultimately we're going to compete on, or will ultimately coming back to what you just mentioned, more the EV for whatever, the middle class, let's say, and also something that's much more affordable, but also not necessarily give you 500 miles, but more reasonable, maybe 300 to 400 miles or something? Where do you see that going?
Yeah, I've had this dilemma actually for a long time because, as I mentioned, it's all about expectations. In around 2016, the Chevy Bolt, for example, came out with a 200-mile car. That was quite an achievement. 200 miles was achieved. The Tesla Model 3, that was supposed to be the promise. That was supposed to be a $35,000 car when you looked at what happened there. And go try to get a $35,000 Model 3 these days, and it just simply doesn't exist. So I think that it's a bit of a halo effect with the performance numbers. I think it's still a retraining effect on the public. As you become an EV owner, somewhere around 250 to 300 miles is quite a sweet spot as an EV owner myself. I rarely take trips that are over 200 miles in a day. I think that as infrastructure improves on the charging side of things, when folks can go out into the world and have that confidence that wherever they're at, there'll be a charger. I know from the old days, how many times have you pulled out of the garage with the low fuel light on in your vehicle, and you're like, well, I'll take care of that a little bit later, right? And that's only just because you have the confidence that there's a fueling station, at every corner. I actually thought of a key indicator would be out there. In the end, the fueling infrastructure is a little bit more of a real estate business than an energy business. Its location. That you would start to see pumps getting slowly but surely replaced by fast chargers. And out here in California, I've actually seen a couple of instances of that, where maybe not on the primary pump island, but now over by the air compressor machine, you'll find tucked in the back, like they're trying to be sly about it, that there's a fast charge station there. So I see as some of the rest of the world sort of adjusts, I think you'll start seeing where a 200 to 300 mile car, for most intents and purposes, for getting around, is probably good enough, and that you may actually start to see vehicle manufacturers offering vehicles with different capacities of batteries. The Lucid Air Dream Edition, for example, achieved something. And I think it was interesting because while they're also a very fast, high performance vehicle, as you mentioned, they also achieved another goal, which was a 500-mile range.
Right.
They, I don't want to call it a publicity stunt, but it was a publicity stunt. They went from LA to San Francisco in one trip, which is quite remarkable.
Yeah, sure.
So maybe in the future, here very soon, you go to the dealership and you negotiate your battery pack size. So I think that's a challenge for us in the engineering world to make that flexibility. Batteries are a little bit bespoke, these days. They're built to fit that envelope of that particular make, model of vehicle. I still think there's a lot of structural changes that can be made through standardization. We're seeing a shift slowly but surely over to purpose-built vehicles that are electric now. I'm not sure if you were familiar with the term compliance car. So, back in, let's say 2010 to 2015 era, you saw compliance cars. Compliance cars were usually small economy vehicles that more or less just checked a box for the OEMs in their offering. They were based on an internal combustion engine vehicle, which meant that the packaging was centered around an engine, transmission, driveline, and exhaust, which is somewhat limiting when it comes to electrification. But now we're seeing purpose-built vehicles. The Lucid, the Tesla vehicles are perfect examples. The ID vehicles from VW. So things are moving around. There's enough commitment from the industry now to redo the body in white and all the other things that make that battery up. So I'd like to see, flexible battery pack sizes, maybe foam inserts in the battery to reduce it, to meet your budget. If it's a commuter car, 200 miles is fine. You're talking $4,000 or $5,000 savings on the sticker price of the car from that, right? But we're not there yet.
Are you a proponent then, so to speak, personally, of, let's say, what NIO does, which is more focused on battery swapping?
Not so much. I think that when you practically look at what's involved with swapping out a battery, the infrastructure and, again, real estate required, I think it's a nice idea, but I think just the practical nature is that the world will push that back.
Okay.
Yeah.
All right, if we dive now a little bit into more of the technology side that you're certainly heavily involved with, and let's say go outside of automotive. I know you're an avid mountain biker. I assume you don't have a battery on your mountain bike, or maybe you do. But you have batteries nowadays on lots of different, let's say, mobility devices, right? And again, we've talked about it before now in cars, heavy duty trucks, off road equipment, machinery, airplanes, ships, you name it, it goes on and on and on. But let's talk a little bit about aviation and what it means to put a battery with its controls, with its safety features, with its many times probably weight constraints and much more additional requirements than what you have on a ground vehicle into production or into a product that then actually also takes flight. Tell me a little bit from a technical side where we are, very brief for where we are today, but where do we need to get to over the next several years to make that technology even more viable for a widespread adoption in the aviation space?
Yeah, certainly. I mean, I think that's the probably single biggest opportunity in transportation in many decades to transition to electric flight. There's certainly some overriding challenges above and beyond what automotive is requiring. Namely the safety aspect. You no longer have the luxury of safely pulling over to the side of the road if you're out of energy. Number two is the weight aspect of flight. It's obviously very weight sensitive, and I think that there is the other aspect, the commercial aspect of flight, that is quite different from your typical passenger vehicle or even commercial truck. Most of the market in at least in light duty automotive is not driven by economics. It's driven more by sentiment and feelings about what type of product a person associates themselves with. Aviation is a much more commercial endeavor. So in order for it to be successful, literally to get off the ground, it has to be commercially viable, right? So those are all challenges that are compounded to be overcome and unseat the incumbent technology, which is fossil fueled internal, external combustion, whatever you want to call it. So those challenges are all intersecting in the aviation space. But that's honestly the exciting part. That's what we do in companies just like ABL, is overcome those obstacles. And the steps are being made. Obviously, with the first flight of the aviation, that was one step towards a commercial product. We know that the shortcomings of cost and weight are there. The low-hanging fruit is being investigated. We're looking at lightweighting. We're looking at improved thermal capabilities to reduce the weight associated with the thermal. I see a huge opportunity in the increase in the voltage that's required. I've always had a rule of thumb: anytime you're exceeding about 500 amps any place in a system, you're probably wanting to go up in voltages at some point, at least somewhere, to get that back down underneath the 500 ampere level. And we're well above that right now with the technology. Most automotive applications are still in the 350 to 400 volt, trucking in the 650 to 900 volt. This first step into aviation is getting up there into the 7 to 900 volt. I personally think that we're going to have to step into the kilovolt range. We're talking 1.3 to 2.5 kilovolt. You start to get some interesting challenges with that. You don't walk around and look at power substations that run hundreds of thousands of volts where everything's packed in tightly together, right? There's a reason for that. Mm-hmm. And those types of issues are going to occur in the aviation as they strive to push higher voltages to be able to reduce weight and increase power density. So, okay. Yes, I think we're on the road to that, just beginning there. Obviously, the chemistry, battery chemistries that are needed to come down the line. We talk about solid state technology, lithium, sulfur, sodium chloride additives. All these things are hopefully 10, 30, 20, 30% improvements. The aviation industry likely needs something like a 50 to 100% improvement over where we're at now to be able to make a viable aviation product. But as I mentioned, we were back at lead acid 40-mile cars only about 15 years ago. So I'm very excited to see where we're at in 15 years from now for aviation.
Tell me a little bit about what your view is. Everybody talks about how the criticality, certainly in the passenger vehicle space, right? We hear it, and we hear it specifically for inverter as it relates to silicon carbide technology. Important for aviation, or not that important for aviation?
I believe it's important. I mean, obviously, every ounce of weight and every watt hour of energy that can be recovered will be done so in aviation. It's a process of what I call shaving triangles. We're doing that all the time. You look at two parameters in any given system, and you're basically shaving small triangles, and what's left over on the floor is the savings, right? Silicon carbide technology is one of those kind of steps. It'll be done simply because the industry is making it commercially possible for that to be done. But I don't think that at the moment the silicon carbide is necessarily the primary enabler. There are some advantages in silicon carbide to the higher voltage aspect, which is potentially a game changer there. But I believe that technology is sufficiently mature already to begin implementation. The next generation of technology that may be on the radar for the aviation is the gallium arsenide solution for the power switch. We're seeing this in the smaller accessory drives, onboard chargers, DC-DC converters. They have a similar, if not better, switching characteristic than the silicon carbide, but are somewhat limited in their ability to scale up in size and voltage. But I think there's a number of companies we've been looking into that are starting to make some headways there. And I think that at some point, the silicon carbide may actually be leapfrogged once those fundamental aspects are figured out, basically.
Okay. Maybe the last question. You work heavily also with the team in California for us on stationary power systems, and mainly on fuel cell based or hydrogen based, using a fuel cell to generate electricity. You don't either store it in a battery or directly then power a backup grid, a IT department, an entire building, whatever it might be. Stationary power systems, right? What about hydrogen or fuel cells for the aerospace? Instead of purely battery, purely electric, how about using essentially an onboard generator that is a hydrogen-based fuel cell generator? Well, what about that for aerospace? What's your view there?
I actually think that for the aerospace, that likely, again, there would potentially be a leapfrog towards basically using hydrogen as a combustible fuel for aviation, aviation. When you look at the numbers to move a passenger airliner across international distances, the energy is quite large. The amount of it almost doesn't really even come down to the actual propulsion and conversion technology. It just comes down to how much energy can you store on that vehicle to be able to traverse those great distances. Hydrogen certainly has that potential. It's got the highest energy density per kilogram of any element, not necessarily by volume, but you could see that with the infrastructure at a airport or international facility, that you could potentially use liquefied hydrogen in some type of turbojet or turboprop type engine. Whether the fuel cell becomes the energy converter to do that or not, I'm not so sure on that, just from the conversion efficiencies and things that we see now. I think for the backup power situations where you have really no limitations or you have moderate limitations in volume and weight, it makes sense. But we're always open if new developments occur or new physics is discovered. Then that's the direction it'll go.
Very good. Thanks, Brian, for your insights, and thanks everyone for tuning in to our latest episode.
My pleasure, Stephan. Thank you very much.
Thanks for listening to Reimagine Mobility Podcast. If you like this episode, please subscribe and tell a friend.